Delaware Tech, Chemistry 100, Chemistry 110, more gas law practice problems. On the first slide, I'm going to show these will be problems that can be used for both Chem 100 and Chem 110. The final slide is just for Chem 110. So here we have three practice problems. Number one, a nitrogen sample has a volume of 250 milliliters at 25 degrees Celsius or centigrade at constant pressure. What is the volume at 95 degrees centigrade? Okay, well, already you can see it's constant pressure. It's a single sample, so that's not going to change number of moles. So we're really just looking at volume and temperature here. And volume and temperature tells us that it's Charles's law we're going to be dealing with. But it really doesn't matter which of the four main gas laws we're talking about. We can always start with the same overall ideal gas equation shown here. So let's just circle that part of our equation. So there's our original ideal gas law equation. And from the problem, we can see that the pressure is constant, so we know P1 equals P2, and therefore we can cancel them. This is a single sample. Nothing's changing as far as the amount of the sample, so we know N1 equals N2, and we're left with Charles's law. And Charles's law, like all of the laws except Boyle's law, is much easier to deal with if you then cross-multiply the two sides so that you get rid of those fractions. And now, this is a very easy equation to allow you to solve for any one of those four variables. In this case, we're being asked for the new volume, V2, so we divide both sides by T1, and we end up with our final equation here. So, let's continue on. We now have the formula that we need in the right form. We have an initial volume. It's in milliliters, but we're not asked to give the volume in a new unit, so we're going to assume that we're still looking for milliliters. So we can leave milliliters alone, though we do have to change the 25 degrees C and the 95 degrees C to Kelvin, as always with gas laws, by adding 273.15 degrees. So our formula will look like this. We plug in 250 mils, we plug in the corrected temperatures, and those are the initial temperature of 298.15 degrees Kelvin and 368.15 degrees Kelvin. And this gives us 308.695 mils. And we know that we should round this to two significant digits. You look at the original problem, and all three numerical values have only 2 sig figs. So our final answer is 310 mils. Looking at the second problem, a sealed sample, so we know for sure that N is not changing, of carbon dioxide gas at constant temperature, so we know temperature is not changing. That only leaves volume and pressure. Occupies a volume of 3.50 liters at 125 kilopascals. So we're given the initial volume and the initial pressure. What pressure is exerted on the gas if the volume is only 2.00 liters? So we have a new volume. So this is clearly Boyle's law. We're only looking at volume and pressure. So we rearrange our original ideal gas law. First we cross out our N and our T because they're not changing, and we're left with Boyle's law, and then we solve for our pressure 2, which is our final pressure. So P2 equals P1 times V1 divided by V2, and now we plug in all our values, keeping the units in place. And you'll notice that at the end, we will have a unit of kilopascals, and that's fine. There's nothing in the question saying to change that unit. So we're going to keep that unit, and you'll notice that each of the values in this problem have 3 significant digits. So the lowest of those 3 is obviously 3 significant digits. So we round our answer to 219 kilopascals because it has 3 sig figs. Number 3, what is the total pressure in kilopascals in a container that contains 342 kilopascals of oxygen, 6.02 atmospheres of hydrogen, and 52 millimeters of mercury of helium. So we can see right away that this is asking for total pressure, and we're being given 3 partial pressures, though you can obviously see that the 3 partial pressures are all in different units, but this is clearly a Dalton's law of partial pressure problem. So first we have to convert each of the gas pressures to the same unit of pressure, and since we're asked for total pressure in kilopascals, that's the unit we're going to use. So first we need to convert the 6.02 atmospheres of hydrogen and the 52 millimeter of mercury of helium. And we can do that as shown in blue here. Now you'll notice with the hydrogen it's a straightforward conversion. We know that 1 atmosphere pressure is the same as 101.325 kilopascals, so we can make a conversion factor that has atmospheres on the bottom, since that's what we're eliminating, and kilopascals on the top, because that's the unit we want to create. So we end up getting 609.98 kilopascals of hydrogen. Notice I'm not rounding the number just yet. We want to avoid rounding errors, so we don't round until the end of the problem. And then if we look at the helium, we're starting with 52 millimeters of mercury of helium, or 52 torr of helium. Now, if you look on your conversion tables, you know that 760 millimeters of mercury is 1 atmosphere. And you know that 101.325 kilopascals is also 1 atmosphere. So instead of using 2 separate conversion factors to convert millimeters of mercury to atmospheres and then atmospheres to kilopascals, we really can just do this in one shot. We know that 760 millimeters of mercury is the same thing as 101.325 kilopascals. They're both equal to 1 atmosphere. So you might as well make one conversion factor. And when we do this, we again put the millimeters of mercury on the bottom because we're removing that and we're creating kilopascals, so that's on the top. And we end up calculating 6.93 kilopascals of helium in this case. And now we have all 3 partial pressures of our gases in kilopascals. Now we just simply use Dalton's law to add the 3 partial pressures together of the oxygen, the hydrogen, and the helium. And now we're just summing these numbers up. And in the end, we have to, since this is an addition, and our lowest quality number is the 342 kilopascals of oxygen. That one has its last significant digit in the ones position, and therefore we round to the ones place, giving us 959 kilopascals. You can think of it as 3 significant figures, but when you're adding or subtracting numbers that have significance, you have to look at the decimal places, not the significant. So let's look at the second page of practice problems. Number 4. How many moles of neon gas are found in 42.8 liters at STP? So this is clearly an STP rule question. We know the conversion factor for STP, at least STP in the United States, uses 1 mole of any gas is equal to 22.4 liters of volume at standard temperature and pressure. That is 0 degrees C, otherwise known as 273.15 degrees Kelvin, and 1 atmosphere of pressure. So that's a simple conversion. We start with what we have, which is 42.8 liters of gas, and we multiply it by our STP conversion. We put liters on the bottom, we put moles on the top, and then you put the numbers in. Remember, always put your units in first in your conversion factor to avoid mistakes. And we calculate that this is equivalent to 1.9107 moles, or if we round it to 3 sig figs, 1.91 moles of neon. And this makes sense because we look at the original volume of gas, 42.8 liters. It's about twice as much as 22.4 liters. So we expect this to be about 2 moles, and sure enough it is. Number 5. Helium gas has a pressure of 3.8 atmospheres at negative 45 degrees C. What pressure will it have at 45 degrees C? That is positive 45 degrees C. So we're looking at a pressure change at two different temperatures. This is clearly an example of Gay-Lussac's or Amundsen's law. And since we're only dealing with changes in P and T, we use Amundsen's formula. But if you don't need to remember Amundsen's formula, as long as you remember the two-condition ideal gas law shown in blue in the beginning of this line, then you cancel out the number and the volume because these are not changing in this problem. So we have P1 over T1 equals P2 over T2. We cross multiply to make our life easier for calculations. And then once we have P1 T2 equals P2 T1, it's very easy to solve for the final pressure P2. So P2 is equal to P1 T2 divided by T1. So you'll notice the T2 is on the top, the T1 is on the bottom, so be careful when you're plugging in your numbers. Also, you've been given two different temperatures in Celsius, and we can never use Celsius in gas laws. We have to use Kelvin. We have to convert it by adding 273.15 to each of those numbers. So we plug those in, and that means that our initial temperature, minus 45 degrees C, is now 228.15 degrees Kelvin. And our final temperature of positive 45 degrees C is now 218.15 degrees Kelvin. The degrees cancel each other. We're left with atmospheres, and we calculate that our final pressure is 5.299 atmospheres. We look back at our original problem. We see 3.8 atmospheres, negative 45 degrees C, positive 45 degrees C, all have 2 sig figs. The lowest of those sig figs is 2 sig figs. So we round our answer to 2 sig figs, or 5.3 atmospheres. Now let's look at the last problem. What is the pressure in atmospheres exerted by 0.156 grams of nitrogen gas, N2 gas, in a 7.4 liter balloon at 85 degrees centigrade? So we can see right away we're probably going to have to make some changes, but let's look at the big picture. We're being asked for pressure. We're given grams, which we know we can convert to moles using the molar mass of nitrogen. We have a volume, and we have a temperature, though it's in centigrade or Celsius, and we need to convert that to Kelvin. So looking at the big picture here, we're being asked for a pressure. We have enough information to get the other three parameters. This is clearly an example of the ideal gas law. So first we need to convert our 0.156 grams of nitrogen to moles of nitrogen, and we need the molar mass to do that. So while it's not worked out in this problem, you can easily determine the molar mass of N2 gas by multiplying 2 times the molar mass of a single nitrogen atom, and that gives you 28.0134 grams of nitrogen gas per 1 mole of nitrogen gas. And I've written it upside down in the conversion factor because we want grams on the bottom and we want moles on the top, so that we end up canceling grams and creating moles. And this allows us to calculate how many moles of nitrogen gas we actually have. And it's a very small number, 0.0055688 moles of nitrogen. And I haven't rounded it. We want to avoid rounding errors. But now we have our number of moles, we have our volume, and we have our temperature, which still needs to be converted to Kelvin. And we can do that in the equation, but let's first look at the ideal gas law equation. PV equals nRT allows us to quickly solve for P. Dividing both sides by V, we get P equals nRT over V. And now we have our equation. We have all our values except our final temperature, and we can begin plugging these numbers in. And we use the appropriate R value. So since this problem is in liters in volume, in atmospheres for pressure, in degrees Kelvin for temperature, and moles for the amount, our unit for R must be liter atmospheres per degree mole. And the number that corresponds to that unit is 0.082057 liter atmosphere per degree mole. If we were using a different pressure unit, we would have to use a different version of the R constant. They're all the same, but they're different units, and therefore they require different numbers. You'll notice I've also converted the 85 degrees C to 258.15 degrees Kelvin. And now we're ready to take our calculator and multiply and divide out in order to determine that we have 0.022116 atmospheres of pressure exerted by this gas. And since in our original problem, the lowest number of sig figs is found in 7.4 liters and 85 degrees C. That's two significant figures. So we round our answer to 2 sig figs, or 0.022 atmospheres of pressure. And we'll stop here.